A small candle 2.5 centimeter in size is placed at 27 centimeter in front of a concave mirror of radius of curvature 36 centimeter. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Describe the nature and size of the image. If the candle is moved closer to the mirror, how would the screen have to be moved? Here we can see a concave mirror of focal length f equals to minus 18 centimeters, since the radius of curvature of the mirror is 36 centimeter, and an object, that is a small candle, is placed in front of the mirror at a distance 27 centimeter. So here object distance u equals to minus 27 centimeter, and focal length of the mirror f1r by 2 equal to minus 18 centimeters, since it is a concave mirror, and height of the object is plus 2.5 centimeter. From mirror's formula, we have 1 by v plus 1 by u sum 1 by f, and we put the values of u and f with proper sign. So we get 1 by v plus 1 by minus 27 equals to 1 by minus 18, and after calculating we get v equals to minus 54 centimeter. So screen should be placed in front of the mirror at a distance of 54 centimeter. As the image distance is negative, so image is formed in front of the mirror at a distance 54 centimeter. Now lateral magnification for mirror m equals to minus v by u. Again we put proper sign of v and u, and we get m equals to minus 2. So image will be real, inverted, and 2 times magnified. That is, height of the image hi equals to 2 into ho, where ho is the height of the object. And we know lateral magnification m equals to hi by ho. So hi equals to 2 into ho, or we get 2 into 2.5 equals to 5 centimeter. Now, if the object is moved from the center of curvature to the focus of the mirror, image moves from center of curvature to infinity. That is, when an object is placed at the center of curvature of a concave mirror, the image is formed at the center of curvature, that is, at the point of the object. Now, if the object is moved to the focus, that is, towards the mirror, the image moves towards infinity, that is, away from the mirror. So, here the screen should be moved away from the mirror. A 4.5 centimeter needle is placed 12 centimeter away from a convex mirror of focal length 15 centimeter. Give the location of the image and the magnification. Describe what happens as the needle is moved further from the mirror. So here we can see that a needle of length 4.5 centimeter is placed in front of a convex mirror at a distance 12 centimeter, and the focal length of the convex mirror is 15 centimeter. So here object distance A is minus 12 centimeter, focal length of the mirror is plus 15 centimeter, and height of the object is plus 4.5 centimeter. From mirror formula, 1 by v plus 1 by u sum 1 by f, and we put the values of u and f with proper sign and get 1 by v plus 1 by minus 12 equals to 1 by 15, and after calculating we get v equals to plus 60 by 9 centimeter or plus 6.7 centimeter. Positive sign of v means the image will be formed behind the mirror. So image will be formed behind the mirror at a distance 6.7 centimeter. Here we can see that image is formed at a distance 6.7 centimeter. Lateral magnification m equals to minus v by u, and if we put the sign of v and u, we get m equals to plus 5 by 9. As the object is moved away from the mirror, the image will also move away from the mirror towards the focus. When the object is at infinity, the image will be formed at the focus of the mirror. A tank is filled with water to a height of 12.5 centimeter. The apparent depth of a needle laying at the bottom of the tank is measured by a microscope to be 9.4 centimeter. What is the refractive index of water? Here we can see that a tank is filled with water up to a height 12.5 centimeter, and there is a needle at the bottom of the tank, and light rays goes from this needle and gets reflected at the water air surface, and the virtual image is formed at a depth 9.4 centimeter. That is, it is the apparent depth of the needle. Here we know that refractive index of water equals to real depth by apparent depth, and real depth is 12.5 centimeter and apparent depth is 9.4 centimeter. So we get mu w equals to 1.33. Now if water is replaced by another liquid of refractive index 1.63, then we can take that mu l equals to 1.63, or 1.63 equals to real depth 12.5 by apparent depth DAL. Here we have taken apparent depth for the liquid is DAL, or DAL equals to 7.67 centimeter. So apparent depth in case of water was 9.4 centimeter, and in case of the liquid it is 7.67 centimeter. So change in apparent depth equals to 1.7 centimeter. So the microscope would have to be moved down by 1.7 centimeter. Figure A and B show refraction of a ray in air incident at 60 degree with normal to a glass air and water air interface respectively. Predict the angle of refraction in glass when angle of incidence in water is 45 degree with the normal to a water glass interface. Here we can see that light rays goes from air to glass, and angle of incidence is 60 degree and angle of refraction is 35 degree. So we can write mu a sin 60 degree equals to mu g sin 35 degree, where mu a and mu g are refractive index of air and glass respectively. Similarly, in case of air water surface, we can write mu a sin 60 degree equals to mu w sin 47 degree. Comparing these two equations, we get mu w sin 47 degree equals to mu g sin 35 degree, or mu w by mu g. After putting the values of sin 35 degree and sin 47 degree, we get 0.78. Now, in case of water glass surface, light rays goes from water to glass, and angle of incidence is 45 degree, and we have to find the angle of refraction. Let angle of refraction be theta. So here, applying Snell's law, we get mu w sin 45 degree equals to mu g sin theta, or sin theta equals to mu w by mu g sin 45 degree. Now we put the values of mu w by mu g, which is 0.78 here, and sin 45 degree 1 by root 2. So we get sin theta equals to 0.78 by root 2, or theta equals to sin inverse 0.55, which gives approximately equal to 33 degree. A small bulb is placed at the bottom of a tank containing water to a depth 80 centimeter. What is the area of the surface of water through which light from the bulb can emerge out? Refractive index of water is 1.33. Here we can see that B is the bulb which is at a depth h in water, and we have to find the radius r, that is OC, and therefore we have to find the area of this circle or circular portion through which light comes out from water to air. Now at point C, if we apply Snell's law, we can have mu w sin theta c equals to 1 into sine 90 degree. Here we have taken the refractive index of air to be 1, and here angle of refraction is 90 degree. So we get sine theta c equals to 1 by mu w equal to 3 by 4, where theta c is the critical angle. Or cos theta c equal to root over 1 minus sine square theta c, and after calculating we get root 7 by 4. Or dividing first equation by second equation, we get tan theta c equals to 3 by root 7. Now from right angle triangle BOC, we can see that tan theta c equals to r by h. So r by h equals to 3 by root 7, or r equals to h into 3 by root 7. If we put the value of h, which is 80 centimeter equal to 0.8 meter, we get r equals to 0.91 meter. So area of this circle through which light comes out from water to air is equal to A equals to pi r square, and after putting the value of r, we get 2.6 meters square. A prism is made of glass of unknown refractive index. A parallel beam of light is incident on a face of the prism. The angle of minimum deviation is measured to be 40 degree. What is the refractive index of the material of the prism? The refractive angle of the prism is 60 degree. So here delta m, that is angle of minimum deviation, is given as 40 degree, and refracting angle of the prism is 60 degree. Let mu g be the refractive index of the material of the prism, and we know the equation mu g equals to sine a plus delta m by 2 by sine a by 2. If we put the value of a and delta m, then we get mu g equals to sine 50 degree by sine 30 degree, and after putting the value of sine 50 degree and sine 30 degree, we get 1.53. Mu g equals to 1.53. When the prism is placed in water, its refractive index with respect to water is W mu g, which is equal to mu g by mu w. Now we have already calculated mu g as 1.53 and mu w is given 1.33. So we get W mu g equals to 1.15. Let delta mw is the new angle of minimum deviation. So again, we use the equation W mu g equals to sine a plus delta mw by 2 by sine a by 2, or sine 60 degree plus delta mw by 2 by sine 60 degree by 2, where we have put the value of a, which is equal to 60 degree. Therefore sine 60 degree plus delta mw by 2 equals to W mu g into sine 30 degree, and sine 30 degree equals to 0.5, and W mu g we have already calculated 1.15. So after calculation, we get 60 degree plus delta mw by 2 equals to sine inverse 0.575, which is equal to 35 degree. So we get delta mw equals to 10 degree. Double convex lenses are to be manufactured from a glass of refractive index 1.55 with both faces of the same radius of curvature. What is the radius of curvature required if the focal length to be 20 centimeter? Here we can see a double convex lens with radius of curvature R1 and R2 of the first and second surface. We have taken this is the first surface and this is second surface. Now radius of curvature of the first surface is positive and radius of curvature of the second surface is negative for a double convex lens. Here we have been told that the radius of curvature of the two surfaces are equal. So we have taken R1 equals to plus R and R2 equals to minus R. Since both faces of the lens have same radius of curvature, we have taken R1 equals to plus R and R2 equals to minus R. From lens maker's formula, we know 1 by F equals to mu g minus 1 by R1 minus 1 by R2, where mu g is the refractive index of the material of the lens and F is the focal length of the lens. We put the value of F, which is plus 20 centimeter, mu g, which is 1.55, and R1 and R2 both are equal to R, but R1 with a plus sign and R2 with a minus sign. So we get r equals to 22 centimeter. A beam of light converges at a point P. Now a lens is placed in the path of the convergent beam 12 centimeter from P. At what point does the beam converge if the lens, a convex lens of focal length 20 centimeter, this is the first case, and a concave lens of focal length 16 centimeter, which is the second case. First case, when a convex lens is placed, P is the virtual object and I is the real image. Before point P, we have placed the convex lens. So here P behaves as a virtual object and its image is I. Here focal length of the lens is given as 20 centimeter. So we have written f equals to plus 20 centimeter and u is plus 12 centimeter since the object is virtual. From lens formula 1 by v minus 1 by u summon 1 by f, we get 1 by v minus 1 by plus 12 equals to 1 by plus 20, and after calculation we get v equals to plus 60 by 8 or plus 7.5 centimeter. So image is real and is formed 7.5 centimeter right to the lens. When a concave lens is placed, P behaves as a virtual object and I is the image. We do not know whether the image is real or virtual. We have to calculate V, and after calculating V we can say whether the image is virtual or real. So here F is minus 16 centimeter since the lens is a concave lens, and U is plus 12 centimeter since P behaves as a virtual object. From lens formula we put these values and we get V equals to plus 48 centimeter. So image is real and is formed at the right side of the lens at a distance of 48 centimeter. An object of size 3 centimeter is placed 14 centimeter in front of a concave lens of focal length 21 centimeter. Describe the image produced by the lens. What happens if the object is moved further away from the lens? So here we are given that u equals to minus 14 centimeters since the object is placed in front of the lens, and f equals to minus 21 centimeter. It is a concave lens and the height of the or size of the object is 3 centimeter, that is HO equals to 3 centimeter. From lens formula, if we put the values of f and u, we get v equals to minus 8.4 centimeter. We can see that light rays from this object are refracted through the lens and forms image at a distance 8.4 centimeter in front of the lens. Lateral magnification m equals to v by u. In case of lens, it is v by u, not minus v by u as in case of mirror. So we get m equals to 0.6 or hi by ho equals to 0.6 or hi equals to 0.6 into ho, and after calculation we get 1.8 centimeter. So image is virtual, erect and diminished in size, that is 1.8 centimeter in size. As the object is moved further away from the lens, the image also moves away from the lens towards focus F. It is the focus F of the lens. As the object is moved away from the lens, the image also moves away from the lens towards focus. When the object is at infinity, the image is formed at focus F. In this case, the image is always formed between focus and optical center of the lens. What is the focal length of a convex lens of focal length 30 centimeter in contact with a concave lens of focal length 20 centimeter? Is this system a converging or a diverging lens? Ignore thickness of the lens. here we can see a combination of a concave and a convex lens of focal length 20 centimeter and 30 centimeter respectively, but focal length of concave lens is negative and convex lens is positive. And the equivalent focal length of this system f is given by 1 by f equals to 1 by f1 plus 1 by f2. And if we put the values of f1 and f2 with proper sign, we get f equals to minus 60 centimeter. Since the focal length of the combined system is negative, so it behaves like a diverging lens.